So, for question 3, we have, what is a pH of a 0.0095 molarity solution of acetic acid, given that the Ka value is that much? So we're given 0.0095 molarity, and they do give us acetic acid, and they give us that the Ka is equal to 1.76 times 10 to the negative 5. So for this, it's going to take a few steps, but the goal is to find out how much of that acetic acid actually associated to hydronium, so H3O, which represents our acid. So we can just draw a quick formula here. We have HCH3CO2 plus H2O. So that's not going to be factored in because it's just the solvent. And that turns into CH3CO2 minus, okay, that is our conjugate base, plus H3O, that is water's conjugate acid. So the reason why I drew this out is because what we need here is an ice table. And the ice table is needed because it represents this formula. We have that Ka is equal to the concentration of the products, so that would be CH3CO2 minus times H3O plus over the concentration of the reactants. But the key thing is here is that we do not include the solvents. We don't include like the liquid, which is water in this case. In this case, that's just going to be HC3CO2. Okay? So that's what we have here. And in order to solve for the H3O, that's where we need the ice table, which stands for initial, change, and equilibrium. So bringing it down exactly, we said we were given 0.0095 concentration of acetic acid. And water doesn't count, we can just cross that out. And now, for the CH3CO2 minus, the conjugate base of acetic acid, we just assume that we started at 0. And same thing with the hydronium, that we just started at 0. The change, based on the formula above, will be that for every loss of X here, of the acid, these two will gain an X. So what we have here in the formula is 0.0095 minus X, and then we have just X and X here. We can actually use this and plug into our formula to figure out the Ka. Alright, and 5 divided by, just doing a quick math about the Ka relationship with the concentration, because if there's a big enough difference between concentration and the Ka, we can drop the X. So what I'm doing here is finding out if there is a big enough concentration difference. And unfortunately, in this case, there is not. So in this case, we're going to have to apply our quadratic formula. And I'll show you what I mean when I get there. But just as a heads up, what I did was divide the 0.095, well 0095, by the Ka. And if the difference was less than 1,000 times greater, we cannot neglect the change that will happen to the concentration of the starting acid. So that being said, we have Ka is equal to X squared, because both these are X's, over 0.0095 minus X. So now we start multiplying across just to be able to now have an equation. We have 0.0095 Ka minus XKa, or KAX, is equal to X squared. And then we move it over, and we have X squared plus KAX minus 0.0095 Ka is equal to 0. And here is where we would need our quadratic equation of the negative b. I'll just write it down. We have negative b, well in this case, Ka is our b, so negative Ka plus or minus the square root of Ka squared plus, the reason why I say plus, because typically it's minus 4ac, but as you can see here, the c here is a negative value. So it's going to be, and the a is a 1, so that makes it a little bit easier. We have 4 times 0.0095, and the a was 1, but we can't forget the ka as well, because the whole thing is a c. This whole thing is c. And then divided by 2a. So let's just start plugging it in. I just didn't want to have to keep writing the ka number. But let's solve first what's under the square root. We have 1.76 times 10 to the negative 5. We're going to square that, and then we're going to do plus 4 times 0.0095 times the ka value, which is 1.76 times 10 to the negative 5. We get a very small number. Nonetheless, we have to do the square root of it. Okay, still a small number. Not much we can do with it just yet. And then we have negative ka plus or minus this value. Okay, so now we're going to have a negative ka plus that. So that's going to be, we're going to assume first is a plus, and we're going to use that ka value. So plus negative of that, and we get, and then 2a, sorry, don't know why I have a there still. A is 1, so it's just a 2. So we divide by 2, and our first answer is 1, 2, 3, 4. So it's pretty much 4 times 10 to the negative 4 for x. That's our first number that I was able to get. And then the second number, which should make sense, should be a negative, which is something that we don't use. Because when we solve the quadratic equation, most times we end up with one answer that's work and one answer that doesn't, because you cannot produce a negative amount of product. So now we're going to have that same number, put a negative in front of it. Okay, and then we're going to now add that negative ka, and then divide by 2. And this one we have another answer of 1, 2, 3, 4. 4.18 times 10 to the negative 4, or negative 4.18. So with that being said, based on these two answers, the only one that works is this one. 4 times 10 to a negative 4. That is our theoretical amount of x that's produced. So with that being said, if I plug this in theoretically, if I square this 4, well, 4 times 10 to the negative 4, I should, and then divide that by 0.0095 minus that same number, I should get a ka of perfect, of the 1.76 times 10 to the negative 5, which I do. So this is a good x to use. So that means x is equal to that, but that more importantly means that the concentration of H3O plus is equal to 4 times 10 to a negative 4. So now what does it mean for pH? For this, we have to use our formula of pH is equal to negative log of H3O plus. So let's go ahead and do that. So let's pull back that number. Okay, and negative log of that. And we get that the pH, based on the 4 times 10 to the negative 4, is equal to 3.397 or 3.40. Around there, once we have rounded. Okay? So, that is how I solved for the pH. So the first thing I did was just make sure I had the Ka formula, did my ice table, did the quadratic equation because there wasn't a big enough difference between the concentration, the initial concentration, and the Ka, and then I was able to now find my x and then use the negative log of H3O on it, which I got my pH of 3.40. So see how our colleague did. Ice table, perfect, and then they did the quadratic equation, it seems. They got 4 times 10 to the negative 4, and yep, pH of 3.40. So this is correct. So that being said, let's move on to question number 4 for tonight.